Good evening, everyone. My name is Douglas Sprang, and I lead the Energy and Environment series for the MIT Club of Northern California. I am delighted to kick off our fourth event of the 2022-23 season, featuring top speakers in the fields of renewable energy, climate change, electric vehicles, and, ironically for the moment, drought in California. Tonight, we are kicking off a new series of events involving hydrogen, an emerging class of renewable energy. We could spend a lot of time discussing hydrogen vehicles, but honestly, hydrogen fits many other applications better and doubles as storage medium as well. And because this is a new area, we have titled our kickoff event Hydrogen 101, because it will cover a lot of the basics we'll build upon in future events. Our speakers this evening are pioneers of the industry. Brian Pivovar, a senior research fellow at the National Renewable Energy Lab, otherwise known as NREL, and Steve O'Rourke, Chief Development Officer for JERA Americas, the US-based subsidiary of Japan's largest power and energy company. We have enabled live Q&A, and I'll do my best to get your questions to our moderator to add to the many excellent questions we got from online registration. But we won't be able to get to all of them due to tonight's large audience. Now, let's kick off tonight's program. I'll be back at the end to close things out, but at this time, I would like to introduce our moderator and the program leader of our hydrogen series, Nitin Vaish, a graduate of MIT's Sloan School of Management, who will orchestrate tonight's fireside chat. Take it away, Nitin.
Awesome. Thank you, Doug. Good evening. Greetings, everybody. My name is Nitin Vaish, and as Doug said, I lead the hydrogen series at the club. I'm super thrilled, actually, to host this event in a hydrogen series. I'll make a couple of quick opening remarks and then have our speakers come in one by one. And then we'll have ample of time for Q&A in the end. I've been in the energy sector for almost 2 decades now, and I've played a small role in different industries, including solar and lithium-ion batteries. And I think what is happening in the hydrogen sector is super interesting and analogous to those industries as they got formed and scaled. Just to get a couple of baseline data points. Currently in the world, we produce about 70 million tons of hydrogen globally, and practically all of it is produced by steam methane reforming, or gray hydrogen, which has higher carbon footprint. Practically all of this hydrogen is being used for refining and ammonia production. Now, that is the baseline, but once you start looking to the future, hydrogen will be a key element for decarbonization. And if you look at analysts and their projections, a couple of data points are Goldman Sachs estimates that by 2050, hydrogen economy will be about $12 trillion globally. Same numbers from Bank of America, about $11 trillion. Point being that we are starting off at the infancy stage of the industry, which is bound to grow by orders of magnitude in next decade, few decades. As that happens, number of building blocks from how we make hydrogen, how we store hydrogen, how we transport, and ultimately how we use hydrogen, all of those building blocks have to come together. It's a pretty interesting puzzle and a lot to unpack. And I'm super thrilled to have 2 of the leading experts in the industry to come and share their insights with us. First of them is Dr. Brian Pivovar. Brian is a senior research fellow at NREL. He is also director of US Department of Energy H2New program. He is the leading authority in the area of hydrogen and fuel cells, has published more than 150 papers with more than 10,000 citations. Brian was born and raised in Kenosha, Wisconsin, father of 2, and he jokes that he is still trying to figure out what he'll do when he grows up, but he has become more deliberate in what he chooses to do. This evening, we are so glad that Brian chose to spend time with us. With that, Brian, I'll pass the ball to you to kick us off and talk about technology and make us smarter.
Thanks, Nitin. It's a pleasure to be here. I'm going to start sharing my screen. Is that appropriate for everybody?
Yes, it is, Brian.
Perfect. So I didn't necessarily come to hydrogen by design, but I've spent almost 30 years in the hydrogen field at this point in time. And being at NREL has really been interesting. I've been there for the last 15 years and I've seen wind and solar really take off. And I see parallels in what's happening to hydrogen. I often talk about the 2010s as the decade of wind and solar and the 2020s as the decade of hydrogen. And I want to talk to you guys about why that is and how that is. And so there's just a few things here. Anybody who's unaware of the Hydrogen Council, reference some other studies, that have even bigger global revenues by 2050. But 18% of total global energy is one of the projections for hydrogen by 2050. And there's really a global race on for hydrogen right now. You can see it across the globe. And the reasons for that are things that I'll get to going forward. In the US, some of the most exciting things have happened in the last couple of years. The first energy Earthshot that came out of the Department of Energy was the Hydrogen Energy Earthshot. It has this 111 moniker for $1 for 1 kilogram of clean hydrogen in a decade. So by 2031, how do we get the cost down to $1 a kilogram? You'll also see things where I talk about getting the cost down to $2 per kilogram. That's where markets start to pick up on this. By the time you get down to $1 per kilogram, the market gets much bigger. And there's different ways that this fits in. And hopefully at the end of this, you have a better idea of how some of those things fit together. Listening to the president talk about hydrogen and listen to the Secretary of Energy talk very positively about hydrogen. Those are things I've never heard really the president before this president really talk about hydrogen that way. And secretaries of energy for a while had neglected hydrogen or thought maybe it wasn't the key piece of this energy puzzle that it really turns out to be. And so this is just the hydrogen shot. One of the things that's come out of these energy Earthshots that's interesting and important is in the bipartisan infrastructure law, there was $9.5 billion for clean hydrogen. $8 billion of that is for these regional clean hydrogen hubs. And that's really about putting steel in the ground and making these things at scale. And it's critically important, and the infrastructure part of that's a really key ask. But then there's this other $1 billion for electrolysis research and development, another $500 million for manufacturing and recycling R&D. Those are more of the research areas, and the $1 billion in particular leads into this H2 New consortium that I'm the director of that I'll talk a little bit about. As part of the big announcements, there was a number of different workshops, and there's looking at power electronics, alkaline electrolysis, bulk storage of gaseous hydrogen, liquid hydrogen, high temperature electrolysis, polymer electrolyte membrane electrolysis, and manufacturing recycling. These are all online. There's reports and workshop findings. Anybody who wants to find out more about those now exist. There is a notice of intent out from the Department of Energy for $750 million for work in this area. So there's a lot of industry and academics who are also moving in these directions going forward. Usually when I first start talking about hydrogen, I'll bring up this bubble chart. It's gone through different iterations. But what this basically tries to do is it tries to describe the energy system as it exists and how hydrogen compares to other things that are in it. So if you look at the left side of this chart, you see renewables, nuclear, and fossil, and this is our energy generation sources. If you look at the big circles that are the electricity grid infrastructure, the natural gas infrastructure, I've added another one that's a hydrogen infrastructure to talk about how hydrogen can create an infrastructure that's parallel to natural gas and electricity, but then can service other areas as well. In this bubble chart, you'll see from electricity, you can make hydrogen, and from hydrogen, you can make electricity. Today, we actually get most of our hydrogen from natural gas, but there's also a number of processes that take hydrogen and CO2 and turn it back to natural gas. So there's this connection between all of these infrastructures. But on the far right, we have the areas that are light blue are transportation related, and purple are industry. And as we look at a future that becomes more electrified, it's easiest to do this on things that are directly connected to the grid. What the hardest thing to make clean and to decarbonize is transportation and industry. And that's really where hydrogen comes in. So hydrogen can be used directly in fuel cells to power transportation. It can be reacted with CO2 to make synthetic fuels. And it's often used in this way to do things like upgrade oil and biomass. Upgrading oil is the largest use of hydrogen on the planet today. Nitin talked about the 70 million metric tons, maybe 40 million of that is related to biomass. Another 30 million metric tons, or the second largest use, is to create ammonia and fertilizer. So hydrogen plus nitrogen can give you ammonia, and that's how hydrogen's basically used today. But we're also looking how to replace things like coal in metals production to make it cleaner and less carbon intense. About 6% of global emissions of CO2 come from iron refining or steel production. And other chemical processes can also be driven with hydrogen. And hydrogen can also be used for its thermal value in much the way that we use natural gas today to provide heat for different areas. So a lot of this is how do you take the things on the left-hand side and the shifting aspects of the renewable nuclear fossil mix, and then do these other things that are difficult to decarbonize. So just a brief summary of some of these attributes of hydrogen, or hydrogen at scale, which is the vision that the Department of Energy uses to promote hydrogen, is hydrogen allows this cross-sectoral and cross-temporal energy impact. So you can move energy across distances, across sectors, and across space. And then you can also, hydrogen is unique in its ability to enable clean and efficient end use. And that's really a big plus to this, because you can use hydrogen in low temperature fuel cells where you can't use other fuels the same way. This gives a lot of benefits. Probably the biggest one are the environmental benefits, air and water. One of the questions I get a lot is, how much water will this take? We have droughts in places like California. And there's a couple of analogies I like to use. For a household, one flush of the toilet is how much water you need to power that household for the day. And if you flush that toilet again, that's how much water would be needed for the rest of their transportation uses. If you actually implemented hydrogen at scale, what you'd find is that you'd actually have a 90% water savings, even though you need the water to make the hydrogen to make this go. Most of the water that's used in energy applications is used for cooling of large thermal plants. And that goes away, and it gives you a large benefit in terms of water. A lot of the air benefits are thought about in terms of CO2 emissions and greenhouse gas, but at least as large of a driving force for me is you can avoid combustion in terms of transportation, which is related to particulate matter and NOx. And so in places, especially in California and dense urban areas where local air quality is an issue, you can't make internal combustion engines clean enough, but hydrogen fuel cell and battery vehicles are inherently zero emissions. Fuel cell vehicles will emit water, but it's actually too clean to drink. But as soon as it hits the environment, it mixes with other things, and it's absolutely fine. Other part of this is getting all these benefits in a single energy system is a significantly enhancement of the value proposition. So you're not just getting one thing, you're basically getting everything. And the way that the Department of Energy tries to approach this is to break up what needs to be done into hydrogen, because we need to make hydrogen better, we need to move and store it better, and we need to use it better. And the national labs are doing a lot to help de-risk the technologies and evolve the early parts of this. In the next slides, I'll talk specifically about these subcategories. I put move and store together, but make and use will all be independently discussed. So on the use side, that's this part of the bubble chart where we have the transportation, the industry, the heating, and even back to power generation. In the upper right corner, there's basically different market studies that we've done at NREL about the technological potential for hydrogen in different applications. And if you see this, there's things like transportation, refining ammonia and biofuels that have the highest value proposition for the hydrogen. And then things like metals, ammonia at different scales, synthetic fuels, those are all the highest value propositions for hydrogen. And this chart basically says, this is how much you can sell into the US market if you can make hydrogen at different levels. And you can see there's some things like seasonal storage that won't kick in until very much below $1 per kilogram. And so there's some markets that are going to be the first to hit, and then there's going to be some that are the last to hit. And what's important about this is that transportation are the strongest economic sectors for hydrogen, but they're also the most difficult to decarbonize or make non-emitting. Many of the processes that are there could be electrochemical, but they're almost all difficult or impossible to fully electrify. You can't make ammonia without hydrogen, is basically what it comes down to. There's no direct way to do it with just electricity. The R&D needs are still significant in this area, but they've been hit on for a long time. So this is my only use slide. Light duty vehicles have shown a very high propensity to be well performing on lithium batteries. And the role for fuel cells in the light duty sector is still to be determined. But in the heavy duty sector, there's really not a good alternative to hydrogen to hauling long distance freight over continental distances, either within trains or more likely by truck. It's also the pathway to ammonia. There's a lot of work going on with how do you do metals, steel in particular, because it's the big sink within the metals group. And then there's even parts of this, fuel cells are really an advantage for hydrogen, but there's this ability to mix hydrogen with natural gas to decrease the carbon intensity and run it through turbines or burners, or even run hydrogen completely pure through burners and turbines. So there's a bunch of different areas within the use side that are seeing ongoing research, but it's not the biggest focal point going forward. Moving and storing is the next one I'll talk about. And in this picture, I talk about a different part of the bubble chart, and I talk about, these are two pictures. The first one is the electric grid in the middle, and the right one's the natural gas grid. But I think that I could tell you that either was either, and you wouldn't necessarily know the difference between the two, because where our energy runs between population centers, where the energy is generated, they have similar aspects in mind. In one case, we use pipelines to transport. In the other case, we use wire. Hydrogen has a very limited infrastructure. There are 1,600 miles of hydrogen pipeline in the country right now and 3 salt cavern storage, but it's almost nothing compared to what we have for these other energy vectors. And what you'll see is that hydrogen is very analogous to natural gas. And I'm going to hit on that a while, because really to make hydrogen as ubiquitous as possible, we have to create the parallel to what the natural gas system's doing. Natural gas is only able to be handled the way it is because we have this $500 billion investment, which allows us to move it economically. There's been some more recent work that talks about transmission of energy costs. And this plot right here basically highlights that if you have liquids, so an oil pipeline, an ethanol pipeline, or a methanol pipeline, they're energy dense, they move energy very, very cost effectively. If you switch from a liquid to a gas, there's an add-on. So natural gas is more expensive than ethanol or methanol, which don't have the same energy density as oil. So there's an increase in cost. And hydrogen has a slightly lower energy density, but it's about a 30% add-on compared to natural gas. There's some materials that you can use for natural gas that you can't use for hydrogen. But hydrogen is only 1/3 the volumetric energy density of natural gas, but it also is 1/3 the viscosity. So it moves through the pipes faster to help offset that difference. And so nominally, I tend to think about 30% more expensive on an energy basis. but it's just on the transportation part. It's not on the fuel cost. If you think about your natural gas bill, most of what you're paying for is actually the cost of the fuel, and only a small portion of it has to do with the infrastructure to move it around. So it's a nominal cost adder within the prices of the energy that you're consuming. We've done other modeling at NREL, and this one on the top left talks about supply and demand. The supply looks at where we have some of the cheapest renewable energy in the country, and what you'll notice is that it comes from the grain belt, and it has to do with the US being kind of the Saudi Arabia of wind, and wind being the most economic renewable energy that we have. But then you can see in the demand side how we use everything at the two coasts and along, well, the East Coast, the West Coast, and along the Gulf Coast. And so the question is how's the most economic way to build that and move it out? We have programs that basically review all the options and come up with the optimized ones. And what you can see is that most of that picture on the right is blue. And that's basically for green, it's gaseous hydrogen pipelines. So the ability to basically produce the hydrogen in those locations, you could have produced electricity, transported the electricity, and then produced hydrogen somewhere else. But the model tells you that's not the economic way to do it. The economic way to do it is actually to produce the hydrogen locally and then distribute the hydrogen, because of the much greater efficiency of moving energy as hydrogen than moving energy as electricity. There's an additional part of this, which is actually just the pragmatic aspect of building a lot of new electricity transmission that likely isn't likely. I've gone on to things like Google Maps, and I look at what the biggest power generation sources are in the country. And we have some things that are around 4 gigawatts, and then one that can get up to 7 gigawatts. And you can look at the high voltage transmission towers that are around them and look at satellite views of them. And basically what it comes down to is each one of those towers can carry up to about 1 gigawatt of power. But that doesn't include any storage, because wires only have transmission. They don't have any inherent storage capability. Pumped hydro and batteries have some ability to help buffer that, but they're really limited, and they're basically best if you can use them every day, because they're an expensive asset. And if they're not being cycled all the time, pumped hydro is a little bit better than batteries when it comes to that. But with batteries in particular, you really want to use them every day, at least some fraction of their capacity. If you compare that to the energy in a hydrogen pipeline, you can see that just with a modest sized pipe diameter, in natural gas, we go up to 48 inches. I think there may even be some 54-inch pipes. You can get into the tens of gigawatts of transmission very quickly. So rather than needing to build out 20 new high voltage towers to move energy around, you could put a single pipeline where you potentially already have right-of-way allowances to do the exact same amount of energy transmission without any problem. The first ones that go in, it would make sense to make them big and oversize them, because eventually you probably want them. But when they're big and oversized, they actually have extra capacity because they can buffer some of the storage, and that should basically help things out as well. So there's a whole lot of things in this infrastructure part of this, and how to move the moving and storing of hydrogen forward, that are big issues. They've had some workshops from DOE. There's been bulk storage, which looked at subsurface storage and things like liquefaction and concerns about boil off. Subsurface is clearly something that's a long-term need. Liquefied hydrogen has a role in certain markets and could be a midterm option before pipeline systems get built out. But pipeline systems are really the only ones that can get you to economic parity with other things that we're using right now. Hydrogen only is something that I would promote, but HyBlend, which is blending hydrogen into natural gas pipelines, is a consortium that's being led out of NREL that includes a bunch of other things that are going on. Then you can even talk about what it would take to convert existing natural gas infrastructure over to hydrogen. And then there's some other research needs there as well. I'm gonna move on to make, I want to leave at least enough time for this, but basically, when you look at this bubble chart, making, moving, storing, they're all important. But electrolysis is the only one that couples the electrical systems to the hydrogen systems, and it also has the most compelling economics. And so a lot of this is making is the first step, and electrolysis is the most competitive way to go. There's a bunch, there's three main types of electrolyzers. There's alkaline, there's polymer electrolyte membrane. Both of those are low temperature. They typically run around 80 degrees C or, even less, but we're trying to target higher temperatures like 80 degrees C. And then there's solid oxide. Solid oxide's above 500 degrees C. The alkaline and the polymer electrolyte membrane, or PEM, they basically have this ability to dynamically respond potentially better than the solid oxide do, because some of the thermal challenges about operating at those high temperature ranges, but they're inherently less efficient than the solid oxide. So there's a bunch of different research needs that are needed for both of them. And within H2New, we're taking on all these types of technologies, and we're basically taking on what might be focused on in the cons at some level. I don't want to go into a lot of depth right here, but I can do it later. In H2New itself, our goal is to get to $2 per kilogram projected cost. 2026 is probably what we'll change that number to instead of 2025. But in the near future, basically do the electrolysis advances that basically allow us to get there. And I'm going to go through some of the economics of how that happens or why that happens. We talk a lot in my world about wholesale electricity prices. And here are wholesale electricity prices that existed in 4 different regions of the US in the last 5 years. So Northern Illinois, Southwest Public Service, Palo Verde, and Long Beach. And they have similarities. If you look at the left side, this graph, the hours is 1 for every hour of the year. And that's the wholesale price for how many hours of that year exist. On the left side, you could see that there's some hours of the year, and it depends on location, that can be very expensive on the wholesale market. And then on the right side, you can see in all of these areas, there's at least some hours of the year where the utility will pay you to take the electricity. And then there's these long, flat portions where most of the electricity market's served. And you can see that the cost there can range kind of from 2 to 4 cents a kilowatt. And that's kind of key, because you need 50 kilowatts per kilogram, kilowatt hours per kilogram of hydrogen produced nominally. It's 33 kilowatt hours per kilogram if you're 100% efficient. But when you take inefficiencies into account, you need about 50 kilowatt hours per kilogram. So if your electricity cost you 2 cents, that's $1 per kilogram in the energy cost that you put in. So you're always trying to keep your electricity costs as low as possible to make this work. On the right-hand side, we have much more complicated analyses where we change the capital cost of the electrolysis system. If you went out today and tried to buy an electrolyzer, if you tried to buy a big one, you would probably get it for anywhere from $500 to $800 per kilowatt. If you bought just a couple megawatts, it might be over $1,000 a kilowatt. We need to get those prices down to things that are in the 1 to 2 to 3 or 400 range. And this basically shows you, if you take the electricity prices that were in the Palo Verde region in 2017 and have these capital costs and decide when and how to operate your electrolyzer, if you could get an electrolysis system that was only $100 a kilowatt, you can make $1.50 hydrogen per kilogram. If you had $400 system, it would be $2 per kilogram if you operated it optimally. And so these are the types of analysis we do, and they come back. And some of this comes back to, on the left-hand side here, this is the Palo Verde data, but it's actually put in a location marginal pricing heat map. And that basically allows you to say, if I just want to take the 25% that are the cheapest electrons, that's the top. If I want 50% of the cheapest electricity, it's the middle. And if I want 75% of the cheapest electricity, it's the bottom. And this basically, when we look at this, you can see the impact of solar and wind on this. So the solar, you can easily see as that middle part in each of the bands. And the wind is bigger at night. So if you look at the bottom, you can see that in the morning and at the evening, those are the times where electricity prices are the highest, because demand is high and generation from solar cuts off. This area only had 10% wind and 10% solar penetration during this time frame, but it talks about the trends that'll go forward and how we'd want to run electrolyzers potentially to capitalize and help balance the system. within H2 New, which is this now about $30 million per year consortium that I'm leading that includes a bunch of national labs, we focus on three main tasks: durability of electrolysis systems, performance of electrolysis systems, and how do we scale these things up. It has some of this analysis effort that I've talked about before, but basically we try to tie all those together to move this technology forward. I have hour-long talks on basically every one of these different areas, but I'm not going to go into much detail now. I will talk a little bit about cost projections. So with stack costs, and this is for PEM specifically, we have projections on the left-hand side for what these stacks should cost. And what we find is that we can break it up into components. And on the far left side, we have what we think the current is, the midterm target, and then the ultimate target for this, trying to get down to something that's much closer to $100 per kilowatt off of the $350 range. And there's really three different areas that we focus on. Increasing the efficiency, which really doesn't increase the efficiency, it just allows us to run at a higher current density. Because if we run at a higher current density, say we double the current density, we only need half as many devices, and that's a big cost savings. We also decrease the amount of precious metal that's in there. Historically, we've used a lot of precious metal and we've over-engineered these devices, and we can take a lot of it out, we already know. But how much and how that impacts its durability, we don't know as much. And then if we scale up this technology and create manufacturing processes that have efficiencies of scale, we can bring some of these other costs down. So you can look at these types of analyses that we do, and they work in all these types of factors about what we're focusing on. I'm going to talk a little bit about some materials efforts that we're doing in this. One of the big challenges in PEM systems is that we need iridium. We really haven't found another material that's suitable in this application, and it's not clear to me that we will. There are efforts to basically replace iridium, but it's also looking to see how well we can thrift iridium. And so there's work on supports or novel compositions and different electrode fabrications. We also need improved polymer electrolyte membranes. The selectivity of the current membranes is poor, and there's a mechanical durability aspect of this as you go thin that becomes an issue, because we often want to run these things under differential pressure, because there's a value in having a higher electrochemical compression rate in these systems. Recombination layers are basically, when you make them thin, they start leaking more hydrogen. If the hydrogen gets into the oxygen, it's dangerous. But if you can add recombination catalysts and layers, you can mitigate that. And then the novel porous transport layers are really unique to this system, and they need much more work as well. In the alkaline systems, we're talking about traditional concentrated KOH systems. And if they could be made to operate intermittently at higher pressure with higher current densities, they would become very interesting, because they don't depend on precious metals the same way, or expensive metals. More things are stable in base than they are in strong base than they are in strong acid. And oxides exist in strong base. That is part of the reason for that. The last is this alkaline anion exchange membrane hybrid, where you could work with much lower concentration KOH, or hopefully KOH free systems, but nobody's been able to figure out how to make that work yet. If we could get stable polymers and advanced catalysts, that may be something else that would fit into this. There's a whole bunch of people who are involved in this effort with me, and I just wanted to thank them. And then I would thank you, and I would hand it back to Nitin to pass this along. Thank you very much.
Wow, Brian. Thank you so much. Wow, there's so much to unpack there, and goes without saying, actually, economics is the key. So like having you go through this tour of technology and economics and how to make solution work, I think we'll come back to it and double click in the Q&A also. But let's switch gears slightly and have our next speaker, Steve O'Rourke, come online. And Steve is the Chief Development Officer of JERA Americas. JERA is one of the largest energy and power companies in Japan. Steve has been in the climate and clean tech sector for several decades as an equity analyst, as a financier, as a project developer, He led equity research at Deutsche Bank in the sector, at senior leadership roles at companies like Renew and SunEdison, and is currently leading the efforts at Jira Americas. Steve is joining us from Japan, where he's currently traveling. And a fun fact is, I think after your time at SunEdison, Steve, you took a year off in sabbatical and explored 7,000 islands in the Philippines. And Steve has a unique perspective around this sector, not just on hydrogen, solar, but also a global perspective. So it's thrilled to have you join us, Steve, and have you take it from here.
Thank you. So Nitin, Doug, Serena, all our hosts, thank you. Good evening, and maybe to a couple of you, good morning. It's morning here for me, which actually makes it easier for me. So I sort of find myself here rather serendipitously. The company I represent is one of the newer members of MIT's Energy Initiative. And we joined that about 7 months ago, probably about a year ago, actually. And about 7 or 8 months ago, I was encouraged to give a brief talk at their spring review, which apparently turned out to be somewhat less than terrible. And someone who is probably on this call, who I happen to know from my days on Wall Street, had heard it and had the questionable judgment, perhaps, to ask me to come on this webcast. So I'll do my best not to embarrass him or myself. But first, thank you for having me. It's an honor to be here. And I'd also say, particularly in the company of Brian, who's a real expert in this arena. So a few words about my background. I'm an engineer by formal training, electrical engineering and nuclear engineering. It was a long time ago. I no longer lay claim to that title. I've been in several industries, right? From driving submarines to semiconductor industry, to the software industry, to Wall Street, now in power and energy. How a career progresses is often dictated by sort of a confluence of circumstance that never repeats. So as things have progressed, I now find myself as the Chief Development Officer for Jira Americas. And many of you are probably wondering right now, what's a Jira? And I'll get to that in a moment. But a prefatory comment, we're an infrastructure company, right? And any infrastructure type company, development's job is really the creation of new value. Everything that follows is first to endeavor to prevent the destruction of that value, and second, to try and optimize it over time. And that's typically in a portfolio scenario with many assets. So we do that with a book of business that's in part, hopefully methodical and systematic, although it has risk. And the complement to that is we hunt elephants, right? We look for high risk, high reward. That's part of what I'll talk about today, because hydrogen, in our opinion, is precisely that. And we've already put some chips on the table with respect to it. So this is titled Hydrogen 101. I'm going to talk a bit about something broader within which hydrogen will play a pretty instrumental role. So we talk about decarbonization, right? And we talk about decarbonization via profitable fuel production and power generation at a very large scale. So if we could go to the next page, Serena. So I'm going to talk about a few things. Who is Jira? I'm going to talk about decarbonization pathways. I'm going to have a few thoughts on how we think about the market, specifically with respect to hydrogen. And then we'll consider commercialization, because our job is really to commercialize these technologies and then implement them at a very large scale. So if we could turn to page 4, I think it is, and we'll talk a bit about Jira. Very briefly, so Jira is the largest power company in Japan. It supplies over 30% of the country's power. It's a combination of the generating assets and the fuel assets of the largest, Tokyo Electron Power Corporation, and the third largest utility, Chubu Electric, in Japan. It's also a growth company outside of Japan, predominantly in the US. So most of the pathfinding, in fact, I should probably say virtually all of the pathfinding that we do for decarbonization for next generation technologies, we do that here in the US. And that's because the US is rather well equipped to be able to facilitate that. If we could go to page 5, please. So we participate upstream in natural gas procurement. We move more LNG than any company on the planet with a fleet of very large cargo carriers. We have approximately 80,000 megawatts of generating capacity, of which the majority of that is in Japan. We operate in current fuels, LNG, for example. We also operate thermal power generation, renewable power generation, the future production of low and zero carbon fuels, energy transportation and storage, And we also support new technology development for commercial implementation. In JIRA Americas, we do all of the above, and we're sort of at the tip of the spear when it comes to evaluating new technologies for commercial implementation at scale. So an awful lot of that evaluation work happens here, and the demonstration projects that we would embark upon also tend to happen here in the US. That's all I'll say by background on JIRA. If we could step to the next page. So I'm going to talk about decarbonization pathways. If you could go to page 7 now, Serena, thank you. So before 2020, not too long ago, JIRA was a simpler company. It procured feedstock fuels, gas and coal. It transported them via a fleet of very large cargo carriers. It generated power in thermal power plants, and it traded these feedstock fuels on the global market. The company also had minority interests in some renewable energy platforms in Asia, but that was the gist of the company. And there wasn't a whole lot of thinking towards how do we decarbonize this massive carbon footprint that the company has. It was more about recovering from the Fukushima disaster in 2011. So in 2021, a couple of years ago, JIRA announced its net zero carbon goal by 2050. So the company spent much of that year really digesting what that meant, because that's a rather monumental task to undertake. And JIRA Americas spent much of 22 doing the planning, execution, and believe it or not, the beginning execution on it. So what that resulted in, if we could go to page 8, is this diagram is an attempt to capture the potential decarbonization pathways that we're both evaluating and pursuing at JIRA. The timeline across the top is irrelevant, quite frankly. And the failing of this is that it's linear. It really ought to be structured as more of a spider web, where there's a lot of overlap between assets and opportunities. What we've found is when we operate in many different, let's call them segments of the power and fuel industry, you can't treat them as segments. They all overlap and they all intersect, and they're all kind of inextricably entwined. So where we tend to find the greatest economic opportunity is where the overlap happens, right? That's where we actually find the greatest economic benefit. So we're a power producer, in short. So we look for ways to do so with a minimal carbon footprint going forward. So to the left of sort of the blue and green spaghetti you see in the middle of the chart are the means of production and transportation. To the right are the disposition. It's power generating and it's trading on a global basis. As we assess these decarbonization pathways, we take very few off the table. All of those indicated here could be viable commercially within certain time horizons. So how do we think about prioritizing this stuff? If we start in the middle on the left, we know a lot about natural gas. Methane reformation, large-scale hydrogen production with CO2 sequestration. The technologies exist. We've already announced an early-stage project, and we've done so jointly with ConocoPhillips for blue and green hydrogen production and ammonia synthesis at scale. This will be on the Gulf Coast. We look at electrolysis powered by renewables. Brian had a lot to say about this, and it's critical in our evaluation now. We want to build scale with cost reduction for hydrogen production. Again, we're very deeply involved here, and we have a rather evolved renewables development platform to actually put renewables into the ground. That tends to add some cost when you think about renewables as a partial or a complete contribution for electricity generation for electrolyzers. We then look at transportation and storage. Solving this issue, kind of in my opinion, could be the biggest time gate. It could be the biggest issue. In our opinion, ammonia is likely the leading candidate as a carrier for hydrogen going forward. We're also invested in liquid organic hydrogen carriers. We're invested in a German company. We're evaluating that rather deeply as we speak. We still think that's a little far off. We also look at efficient ammonia cracking at scale. It's an area of great interest for us, both for complete and partial cracking. We've been evaluating several technologies. I won't really say who they are because I don't think I can at this point. And the only other one I'll comment on here is pyrolysis, right? We're very interested in pyrolysis, but it's a lower, and this is methane pyrolysis, but it's a lower priority for us right now because of technology maturity, but it's very important potentially for Japan. It's simply a question of what do you do with all the solid carbon? You generate an enormous amount of carbon byproduct when you actually use CH4 pyrolysis at scale. So we try not to pick winners, right? We'll invest to prove out technology, but we do so kind of with this hopeful intent that we can commercialize the technology at scale. If at any point we believe commercialization becomes unviable, we hit not just roadblocks, but we hit failure mechanisms, in our opinion, not necessarily just technically, but economically, we will kill the effort. If we could turn to page 9. So this leaves us with a lot of questions. The scale of what we're trying to do is very large. Can we do it economically? Can zero carbon fuels compete economically on a cost per MMBTU basis? That's our metric, it's cost per MMBTU. Can we burn ammonia efficiently in a gas turbine? What upgrades are required? What capital upgrades are required? Can we reduce the cost of ammonia cracking and scale it in a reasonable timeframe? So we're evaluating an awful lot of things via feasibility studies, techno-economic analyses, and believe it or not, actual implementation at a smaller scale now. If we could turn to page 10. So a few thoughts on the market, because without a market, we don't deploy capital, right? Everything we do is to deploy capital for profit. If we turn to page 11, and we consider markets for a moment in a very simple diagram here, we start with demand. And the first question is always, is there demand? Can you point to demand somewhere in the world? There is for ammonia, right? And there is emerging for hydrogen at this point. Now, it might be hydrogen as ammonia to begin with, but we're also seeing some demand potentially for hydrogen. A convenient advantage that we, JERA, have is that we're an off-taker as well. And once we get comfortable with technology risk, securing offtake is the single biggest de-risking factor for an investment. If you can secure the offtake, you can finance a project. So 3 regions for demand that we think are becoming real, if you look at it, and these are sort of these red areas. Repower EU is driving some demand within the EEU in Europe. And so this is, they're probably about 10 years ahead of the rest of the world when it comes to the actual attempts to implement hydrogen at some reasonable scale. We see this happening. We also see significant demand for ammonia. And this is driven by some obvious changes in the world over the course of the past year or so. There are several regions, well, I'll make one other comment. In Japan, there is also emerging demand, particularly for ammonia. And I would say that the genesis of that is JERA, the company JERA. We've actually had an RFP out for procurement of ammonia. We've already begun burning ammonia. I'll talk about that in a minute. But for scale applications, we're talking 5 years from now, 2027 and beyond. There may be some in the US as well. I think the US is going to be more emergent here. And an awful lot of what gets produced in the US, we'll talk about that in a moment too, is going to be for export. There are several regions for supply. And this is based upon economic advantages. It's driven really by resources, by infrastructure that already exists, and by policy. And the real question to be asked is, where is production cost the lowest? The last thing I would suggest is you see all these little dotted lines. We have to move the stuff we make if it's done at scale. What people talk about an awful lot is transportation, and by transportation, they mean local transportation, maybe hub and spoke, maybe in a local geography. We're starting to look at transportation. We have to look at transportation on a global scale where we move it in very large quantities because we're thinking about using this, actually going to use this for power applications. If we could turn to page 12. So I suggest there are 3 regions that offer an advantage for hydrogen and ammonia production. It's the US, it's the Middle East, and it's Australia. I then suggest that perhaps the most low-cost producers, the most likely low-cost producer is the US. And this is particularly with the passage with the interestingly named Inflation Reduction Act last year. So in fact, the EEU has been sort of crying foul over this since it was passed, saying it provides the US with an unfair advantage. We'll see how they respond. So why is the US advantaged? Why do we think so? Policy benefits economics, the act that was passed. Natural gas is relatively cheap here, quite cheap here. Pore space for CO2 sequestration is plentiful. Existing infrastructure can be utilized in certain parts of the country. Renewable resources are wildly abundant in this country for green. The big energy and power companies, and this is very important, want to play, and they're starting to play at this point. Geopolitical instability has created offtake opportunities that did not exist a year ago. This is places like the EEU. And lastly, new technology development and commercialization, it happens here in the US more than anywhere else in the world. So what are disadvantages? We have inflation. Inflation is very painful when you start to think about implementation of large-scale projects that are financed, because that means the cost of money goes up and it means you have cost inflation of all the input parameters for that particular project. That's something that is frustrating. We kind of work through that overall. And I think it may slow things down a little bit in the very near term, but some of these very large projects, we're still looking at first cargoes that are still 6-8 years away. We can turn to the next page, please. So people ask the question, is this real? Why is it real this time? Why isn't it the same as 10 or 20 years ago when it was a concept and the concept simply amounted to virtually nothing but talks? So to be more specific, New England is to the US as Japan is to the world. Probably the most difficult place to decarbonize in the US is New England. And I'd suggest also that perhaps the most difficult country to decarbonize in the world is going to be Japan. So if we think about New England and we think about further electrification, it will create demand that renewables will struggle to address. Offshore wind build, I would suggest, is happening a bit more slowly and expensively than a lot of people had thought. And regardless, renewable capacity requires reserve capacity. That typically means thermal plants. Storage will struggle to fill this gap, I think, over the time. To the best of my knowledge, there are no new thermal plants planned for New England. It's quite possible the lights could flicker in the coming years. Load growth plus decarbonization mandates fuels like hydrogen. And the last thing I'll comment here is, I think there's a significant gap between the rhetoric that we hear oftentimes and how these low and zero carbon fuels will actually be produced and delivered. What's missing really is sort of an awareness on a grand scale of a pragmatic approach to deliver and to deliver these low carbon and zero carbon fuels like hydrogen. We could turn to the next page, please. Talk a little bit about commercialization overall. And if we could go to page 15, please. So when you're a very large company with a lot of infrastructure and you want to decarbonize, what do? In a nutshell, it sounds really simple. You get rid of the old stuff, you upgrade what's left and you expand it, and you integrate the new stuff. So and this is where we kind of have to take a little bit of a step back and make a mental transition, right? Early in a new industry's timeline, we speculate a lot, right? We can live in this world of concept where the best you can really hope for is kind of a meeting of the minds, and it's often little more than rhetoric, right? That doesn't really get you anywhere except maybe a speaking slot, at a conference somewhere. If you step into the world of reality where execution on a concept is very simple, it's actually looking at one intractable problem after another and figuring out how to solve them. And once you get to a point where there are no intractable problems left, you've already accomplished something. That's hard. That's really what this is all about. This is where zero carbon fuels like hydrogen and ammonia as a carrier come in. And this is where smart capital allocation is really required. And very importantly, you don't want to do it alone. You share the risk and you bring together certain experiences and expertise that allows you to mitigate the risk as best you can with complementary partners. So when it comes to profitable decarbonization, because anyone can invest their way to bankruptcy, JERA's issue to solve is almost always everyone else's writ large. So we've got a big problem to solve. And so hopefully we'll be up to the task to try and do it. If we could turn to page 16, please. So how big, how large is this? So last fall, we announced a project to be located somewhere on the Gulf Coast of the US. It's a joint venture with ConocoPhillips. It's for a blue and green hydrogen production and ammonia synthesis facility for domestic distribution and export. We indicated that we would have 4 production lines of roughly 2 million tons per year each, and they would be staged and brought online. This would reestablish scale in the industry for ammonia. If JERA was to address all its thermal generation needs in Japan with ammonia, whether it be burning ammonia, whether it be burning hydrogen extracted from ammonia, we'd have to build at least 16 of these 4 train facilities with all the offtake going to JERA. That's a huge capital investment. It's a long time horizon. It's a lot of risk. That won't happen. What actually happens is we will have a mix of fuels and a mix of technology generation. or a mix of generation technologies going forward. All this will contribute, but this is sort of an incubation time for the industry to grow. And I would argue this is arguably a new industry, or at least a branch of a new industry. If we could turn to page 17, please. So in a bit more detail, we've eliminated the old stuff. We've already begun the procurement process for large-scale ammonia supply. Now it's about upgrading what's left. So what have we done so far? And this is another argument to say, is it real now? We think so. We've already begun co-firing ammonia with pulverized coal. And this is in one of our ultra supercritical coal thermal plants in Japan. That plant is probably one of the most expensive plants you can build, and it was built after the Fukushima disaster. And it was to supplement loss of power due to nuclear power in Japan. It's more about supply than anything else, and supply of ammonia before we can transition that to 100% ammonia burn, which is the plan. We have other issues to deal with at that point, NOx, for example, ensuring that we can capture that. We've also begun co-firing hydrogen with natural gas at our Linden cogeneration facility in New Jersey. We can blend up to about 30% now. The limitation is really the availability of hydrogen. The hydrogen we're using is off-spec gas from a refinery, a P66 refinery, on which the power station is co-located. So when we can provide more hydrogen to that, we can ramp that well above 30% as a co-firing. We're also evaluating, partial cracking of ammonia and burning this hydrogen ammonia blend. Initial indications show that flame properties of this, it can be tailored to be a lot like natural gas. Ammonia alone has some pretty poor flame properties, and hydrogen has rather aggressive flame properties. It propagates very quickly, it burns very hot. So when we think about this, now the real question is, and this is a fair amount of the work we're doing on the existing infrastructure, because reuse of existing infrastructure is critically important. What do you need to do for retrofit of flame sheets and combustors on turbines? Very important, and all of this stuff we believe is feasible and doable. We can turn to page 18. So what about hydrogen production, right? Reforming methane is not new. We're actively looking into reforming methane at a large scale. We're looking at carbon capture and sequestration and electrolysis. These are the fundamental technology building blocks that we see for hydrogen production that are necessary. We'll synthesize ammonia based upon a Haber-Bosch process that's been around for over 100 years. I'd suggest that water electrolysis may be the most vexing part of this. It hasn't been done at scale yet. And by scale, I mean at hundreds of megawatts or gigawatt scale. That's what we'd be looking for. Available technologies have their own specific requirements that don't always conform to the desired power sources. So we have to be creative about power sources sometimes. And there's the ongoing debate about whether it's better to move power or move molecules. From a clean slate, it may be moving molecules. When we start to think about infrastructure that presently exists, and we start to look at design of power markets and power prices, it could be moving power. So we're sort of actively involved in trying to assess and calculate precisely what that spider web of a project should look like. So that speaks to defining the optimal configuration for a hydrogen production effort. Do you co-locate it and run with imported power? Or do you put it out in a distributed fashion with localized power generation? It's a lot like planning a collector system for a wind farm on a grand scale. So we're simply evaluating the potential for pyrolysis. It's on the bottom of this page. We know something about methane reformation. We know nothing about CCS, but our partners do. And we, like many, are coming up the learning curve on electrolysis. So this is the front end. This is the production of hydrogen. If we could go to the next page. How do you move it? How do you store it? I think this could be the gating item for implementation at scale. We're an active investor with liquid organic hydrogen carrier technology. We're very active in shipping and storing fuels. What we need are new ships for ammonia. Ones that exist today are too small. We need very large cargo carriers, we think at 65,000 meters cubed or larger. So this is similar to what we actually do today with respect to LNG. We're also rather skeptical of liquid hydrogen, and that's really due to the energy requirements for liquefaction. We know a bit about this from all our LNG experience and all the boil-off losses that you tend to get. And then there are pipelines. As I mentioned, we, like many, we're trying to figure out the comparative economics of moving power or molecules. In some instances, we think pipelines make a lot of sense. In other instances, we're not so sure. And that's an ongoing effort that we hope to be able to provide some more definitive answers within the next 2 to 3 months. We could go to page 20, please. So lastly, how do you get the hydrogen out once it's delivered? We assume it's ammonia at this point, right? We'll crack it. So we're involved in technology evaluations of molecular cracking methods. We believe there's an industrial solution that could probably be implemented in the next 5 years. We also see some very interesting technologies that could offer some dramatic cost reduction in the future. Folks deeply involved in commercializing new technologies, I'll make one comment about technology development and implementation. There's a thumb rule I've heard several times from some very smart technologists. And that is when a company, a technology company, gives you a time horizon for commercialization of a new technology that they have, double it, and you're probably within the ballpark. So what we've begun here on these last few pages is we're building a low carbon, zero carbon fuel supply chain. It's complex, it's hard, requires a lot of capital, and it has to be done in a way that's economically viable. It also has to have a long time horizon. So policy prognostications have to be decadal. They can't be a year or two. We don't know all the answers. We don't know all the numbers yet, but we do have forecasts, and hopefully they're directionally correct because we know for certain they're not absolutely correct. They never are. Why does JERA perhaps feel a little bit more comfortable about marching down this path? It comes down to one thing, really. We're an off-taker, right? We use this stuff and we plan to use this stuff at scale. And as I mentioned previously, perhaps the biggest de-risking element of any project, production project for fuels, is do you have an off-taker? If you have off-takers, you can finance projects. So in short, in many respects, we view this kind of as the beginning of a new industry, or at least kind of the beginning of the branch of an old industry, a new branch of an old industry. We could go to page, next page, please. Just a few comments, right? The goal here is profitable growth rather than ideologically driven bankruptcy. I can point to a lot of companies that went bankrupt or invested their way into bankruptcy. We hope not to do that. What I would say is that decarbonization is real. Capital is being deployed. Zero carbon fuels are required. We view hydrogen as an imperative over time. The fuel mix over time will have hydrogen. The question is how quickly it builds in, how quickly can it build in? Natural gas is not going away anytime soon as a fuel or a feedstock. Timing on all of this is about policy and economics. Return on invested capital is a critical metric for us. Long-term policy determinants, that's what provides you with supply, the supply chain builds overall. What's the big headwind? In my opinion now, it's inflation. It's really inflation and what that does also to the cost of materials and the cost of capital. What are the governing metrics we look at? It's really three. It's cost per MMBTU, the cost of energy, it's cost per megawatt hour, the cost of input electricity, and it's cost per ton of CO2 sequestered. I have no answer on that last one. Hopefully our partners do. We're working very closely with companies like ConocoPhillips on it. The last comment I'll make is that, last couple of comments is, renewables growth, this is wind and solar complemented with storage, for example, it will accelerate with green hydrogen production. I think it will accelerate more than most people think. Transmission and deliverability is going to be a regional issue in the future. Green hydrogen production, I think, is going to eclipse the cost of blue within 10 years. And the last comment I'll make for closing is that I think a realistic view of the introduction of hydrogen and zero carbon fuels into the industry for decarbonization exists. It's a realistic view in the power industry and the energy industry. I think, unfortunately, it still struggles, and it struggles mightily in the public sector. And that's potentially with policy arenas, and also in the public arena. So with that, I'll end my comments. I think that's hopefully less than a half hour, and leave it and turn it back to you, Nitin.
That's awesome, Steve. Thank you. Thank you so much. Scale matters, right? And scale at right cost matters. Maybe like Steve and Brian, if you can come back on, we'll have ample of time for Q&A. We've been answering a bunch of questions actually as they were coming up live as well. But please feel free to jot down your questions. We'll do our best to include whatever we can in next 20, 25 minutes or so. Steve, if you don't mind coming back on on the camera? Oh, awesome.
Sorry.
No worries. And but by the way, like we also got tons of really good questions which were submitted at the time of registration. So I'll be doing my best to pick and choose from them, and also live questions, and have a really good conversation. I'll start off with technology, Brian, if you don't mind. And there was a question which came up around different colors of hydrogen. I know, like you touched upon that briefly. Yes, gray, blue, green, pink. If you don't
Yeah.
mind, like double clicking into what is the TRL status of these technologies, and also like how do these things compare economically, will be a really good way of framing how these technologies rank and stack.
Yeah, there's really basically three primary ones as far as I'm concerned. However, there's a bunch of different colors, and I can talk about some of the other colors potentially, but really there's either a gray or a black. Typically black was for coal reforming, and they made it gray because the carbon intensity is a little bit less for steam methane reforming. But there's basically where you take methane or even carbon or coal out of the ground, you harvest as much hydrogen as you can from it by adding water to it, and then you just release the CO2 that's the byproduct. And so that's either black or gray. And then if you take that same hydrogen, and instead of just releasing the CO2 into the atmosphere, you sequester it, it becomes blue. And then the green is basically if you make it renewably. So if you take renewable electricity and an electrolyzer and you make the hydrogen that way, it would be green. Turquoise would be if you took methane and you basically turned it into coal, or carbon black, which is put into tires, and then took half of you only get half of the hydrogen back out that way, but you don't emit any CO2. I would say that those are nominally there's also some for thermally derived from nuclear, and also a version for hydrogen that you can actually just take out of the ground. So there's other colors and other types of this. There's no universal scale on this.
Cool. Awesome.
Can I suggest a new color?
Of course.
So we came up with this recently. We couldn't use turquoise, so we picked teal. And the reason we picked teal is because we have blue and we have green feeding into an ammonia synthesis plant. So we'll ledger the two, both blue and green, and we decided we'd come up with a teal product that comes out the back end. Various gradations of teal.
There you go. Like the spectrum is expanding around.
A lot of it comes down to the carbon intensity, right? So.
Yeah.
You know, I mean, that's what in the end, a lot of the DOEs focused on low carbon intensity things. And so they have an actual metric. I think it's like 2 grams of CO2 per something or other. I don't remember what the exact metric is, but they have to qualify for some of the things in the hubs, it has to be low carbon intensity. So blue and green are both the focus of what they'll allow.
And like just to follow up on that one, Brian, like you mentioned about hydrogen short $1 a kg by 2030, right? Like as we look at the cost of making hydrogen today, like where do these things rank and stack? Maybe you can like double click on that too.
So what's happened historically is every time an electrolyzer was put out, it was running 24/7 at 100% nameplate capacity until basically it filled up its storage reservoir or something else, and then it would shut off until it was turned on again. And under this 24/7 operation, the other part of this is that you might be paying retail electricity rates or industrial electricity rates, and those are very high. And so what happens is that the way that the economic system is worked, historically 85% of the cost of electrolyzed hydrogen had been in the electricity cost. And you could never make that work. And it doesn't actually necessarily make sense for balancing the energy system that way. You can't work it in the same way. A lot of what I presented was based more on the wholesale rates, which I think are much more reasonable for this.
Mm-hmm.
Somebody's going to have to do this behind the meter in some way where they can take advantage of it. Somebody has to pay for the infrastructure for sure. But how you get to the renewable energy portfolio standards of, say, 100% renewables by 2050, a fallout of putting more renewables on the grid is a lot of times of really low value electricity. And that is an enabling aspect, and also why the synergy of having something like hydrogen coupled to energy system evolving makes a lot of sense in this.
Cool. Thank you. Well, so I'll continue this theme of economics and scale, Steve, if you don't mind, and talk about like a big theme, as both of you have touched upon, is make, transport, and use. And if we start looking at the infrastructure around transportation, you touched upon this in your remarks too. There are a number of things which are evolving, from pipelines to liquid hydrogen to ammonia to LOHC. Maybe if we can talk, and then like in a number of these discussions, two things which come up quite often is economics and safety. If, like, to whatever extent you can share your thoughts around how do these technologies compare both on economic side and also like safety side, we will be really awesome.
Happy to start. So from an economic perspective, let's take a big step back, right? Because right now we have forecasts on a lot of the new technologies that are being built. And we have a learning curve that hopefully will build in for some of these technologies that are already active for some of them, right? So what we tend to do is take a look at things, and I think Brian kind of explained this rather well. You have a technology, that technology will adopt a learning curve. First, you have continuous improvement, shall we say, once you solve all of the science problems and it becomes an engineering issue. Once it's an engineering issue, it becomes a continuous improvement program, and then the learning curve takes over. As the learning curve drives things down, we actually see over the course of the coming 5 years or so, the ability to implement a full value chain. The one catch is shipping. I'll get to that in a moment. To be able to produce and deliver ammonia at scale. Now, ammonia as the carrier for hydrogen. When I think about liquid organic hydrogen carriers, for example, remains to be seen, right? From an economic perspective. Could it be lower? It could potentially be lower, but we also have to understand in far greater detail the costs of a dehydrogenation process for extracting the hydrogen on the back end, right? So we don't know that yet. We don't know that to our satisfaction. So ammonia is the horse we've chosen to initially ride from an economic perspective. The others will then follow. The next question I would simply, try to answer is, what about safety? So we've had this belief that it will be virtually impossible to permit large-scale ammonia storage in densely populated areas in the US, like the LA Basin. Is that true? Perhaps it is. If you look at the middle of the country, though, again, we've had a delivery, storage, use of ammonia for a very long time, right?
Yep.
So an awful lot of the issues when it comes to safety and handling of ammonia, it's well known, and now it's more of making sure people understand the safety characteristics of it, and that it's probably not nearly this horrific material that a lot of people want to think it is. And there are industries here, like the semiconductor industry, that has been using far more horrific gases for a very long time, albeit at a smaller scale and contained, but they're far more deadly. So I actually think the safety issues associated with ammonia can actually be addressed. I also think that the economics are going to be an evolving thing, and what we see is a path right now to move hydrogen to ammonia to export at scale, with one exception we have yet to solve, which is what do we do about the very large cargo carriers? And we're in some pretty deep discussions with some shipbuilders about that as we speak. I'll just stop there. So
Yeah. Anything to add, Brian, on that one?
No, I was thinking that we didn't actually talk about the ammonia pipeline that exists in the country already as well, right? So, it's not that far off a scale from the hydrogen. Maybe it's a little bit bigger, but it's small compared to the other types of pipeline systems. But ammonia pipelines exist in this country as well.
Yeah. And I think like if we just go back for a second to electric vehicles as an example, right? Plenty of fear around like lithium-ion batteries catching fire, but prior to that, we were driving gasoline-based vehicles, and like we have to have the right mindset around this. Understood?
Yeah, I mean, there's 10,000 fuel cell cars driving around California right now. There's 50 fueling stations. People are normal people. They fuel them all the time. A lot of people aren't aware of this, but they're there, and all the car companies are willing to take on the legal risks of it. I like to talk about safety because any energy carrier carries energy. And when you carry energy, you have safety concerns at some level. Hydrogens are slightly different than others. Ammonias are slightly different as well. But none of them are, the biggest problem is public perception and the fact that people aren't used to it. And, you know, there's, for hydrogen's side, there's some unfortunate things like the way it shows up in some movies and the Hindenburg, you know, people who think that a hydrogen bomb is, you know, they don't understand that it's a rare isotope of hydrogen that's been centrifuged and separated in ways, and it's only detonated with a fission nuclear bomb. There's all these things that make hydrogen scary to the public, whereas these other energy carriers would be scary to the public too, that just they've accepted them, right? Because what they give us is too much. The safety of hydrogen isn't much, you know, isn't a lot more different than other energy carriers.
Yeah, clear. Yeah, maybe like let's continue the theme of electric, like batteries, because I was looking at the questions which came up from the audience, and there were a number of questions around comparing electric vehicles to hydrogen-based vehicles. And I think, Brian, you touched upon this in your remarks also, like whether it's for passenger cars, long-haul trucking, and there were quite a few around aviation as well. Maybe like we can double click on that theme, like, okay, where does, in the world of transportation, where does hydrogen actually have a play? And I'm thinking economics here, not just hugging the trees. So given all the work you've been doing, Brian, at NREL and in the ecosystem, what's your perspective?
So there's been a big shift from so hydrogen was almost exclusively just light duty vehicles from the early part of my career, from 1994 up until 2010 or 2008 or something. It was all about light duty vehicles. Now it's all about heavy duty vehicles. And maritime's also possible. Aviation is things that people talk about. Trains is the other one that people talk about a lot. For me, light duty vehicles isn't off the table. Batteries are great, but batteries take a long time to charge. They also don't like to charge when the electricity is cheap and abundant and available. There's also some parking problems, and there's different duty cycles. If you want to run 24/7 and have something that never stops, it's nice to be able to fuel it. A Tesla supercharger can basically charge a vehicle at 6 miles a minute, but a hydrogen basically fuels at 100 miles a minute. So depending on where your application is and some of the logistics, I showed the one curve where basically everybody comes home from work at night, and that's when electricity gets the worst because solar goes away and everybody wants to plug their car in. And that's the worst time to plug your car in. But if you want to control when you have your electricity, that's when you have to plug it in. Hydrogen allows you to decouple that and let you take the energy when you decide to. Nobody wants to buy another battery, stick it at home so that when they come home, they've taken the cheap electricity and then they put it into the other battery that's in the vehicle. So there's a bunch of different challenges about how these things balance. There's a role for batteries. There's a role for increased electrification, but it can only get you so far. And that's where hydrogen is the obvious other solution that needs to fill in the rest of the pie for me.
Cool. Well, so like super interesting actually, and I think the parallels of all these different technologies as they've evolved, I think it's also pretty profound. And I want to go back to you, Steve, like given your experiences in the clean tech sector broadly, like solar developer at scale, right? Way back, like 10, 15 years back, solar as a category was still nascent, but now we're living in a world where we're installing hundreds of gigawatts of solar every year globally. And wind, same thing, but maybe 5, 7 years prior to that. And we are seeing the same thing with electric vehicles and batteries. As you're looking at this world of hydrogen and projects at scale, as the technology is getting de-risked, like how are you seeing the parallels to those technology types? What can we learn from those and make these solutions not just in the lab, but deploy at scale to decarbonize?
Right. So look, I mean, solar and wind, they've had some reasonably long lives now. They've kind of delivered to a degree, but they were new assets added to electricity generation. They didn't necessarily complement existing assets that were already in place. And so existing infrastructure was a little frustrated with that, shall we say, sometimes. Where I see a difference here is there are an enormous number of gas turbine generators around the world generating power, right? We have a great many of them. I think we're the largest buyer of GE turbines on the face of the earth. We see a path to essentially utilize existing infrastructure with an emerging new fuel that will then complement the existing fuels that presently exist. Honestly, that's an easier sell to me than a brand new technology coming in to cannibalize the existing infrastructures that exist. If we think about it that way, I view all of it as a complement. We view this thing as an optimized portfolio of generating assets and the fuels that provide them the power necessary or the energy necessary to generate, right? So when I think about hydrogen and I think about the carriers for hydrogen, when I think about ammonia as potentially a fuel as well, maybe not as great a fuel, we're pretty convinced it will build in. The question really is how quickly it can build in, and that has everything to do with how quickly can you build a supply chain economically, how quickly will the next generation technologies build in for commercial viability such as you can improve those economics. And if that happens, and my inclination is to believe that it will, is it 5 years, is it 10 years, is it 15 or 20? It's a decadal long time horizon we have to look at. But we're pretty well committed to it. And the other comment I'll make is many of the other big energy companies that have been accused of things like greenwashing on a regular basis, some of which is probably well earned, are also very involved in next generation fuels, low carbon fuels, zero carbon fuels. Part of it is not simply because they see the writing on the wall, it's because they actually see the economic benefit over time to do so. And when you think about certain companies, for example, we work with ConocoPhillips on a regular basis based upon this joint venture we're working on. They have a carbon capture and sequestration business. It's an independent business. This complements what we do. So they find a great deal of complementarity in what we do and what they do, but you would think that hydrogen production and investment in renewables is anathema to a company like ConocoPhillips. 5 years ago, maybe it was. Today, it's not. I can tell you that. So I actually see it building in. I wish I could tell you exactly when. Time will tell. What I will say is we're looking at first cargoes at the end of the decade, 28 to 30.
Awesome. Awesome.
So we'll see.
Cool. And I think as we're building these things up, I'm looking at the questions which were pre-submitted. Supply chain also has to be built. And I think given what is happening in the world, it's pretty chaotic to say the least. So I think this might be for both of you. Please feel free. But when we look at hydrogen industry, like at scale and supply chain, which needs to be built, whether it's from iridium, platinum, in terms of catalyst, all the way to like power electronics, systems, steels and pipes. Like, what are we saying? Like, what the question actually is, do any of these components or machines need to be imported from overseas? And like, how can US be self-reliant, if you will, as we build this hydrogen economy, at least in the country? So either of you feel free.
I don't mind taking that one on. I
Yeah.
mean, the amount of iridium and platinum that are domestically sourced is almost none. But that's raw material. It doesn't necessarily come to a critical aspect of where manufacturing, where value add comes on afterwards. And so there's no reason they couldn't be manufactured here, but they're going to be manufactured globally. And they're probably going to be manufactured most in the locations where the demand for them is the highest. But much like cars are typically made where they're being sold. I mean, some do get exported and some get imported, but that percentage has gone down over time as companies have become more global. And that's likely to be the case. There's not a good reason to do manufacturing in one area versus the other. which companies own the technology and deliver it, and what's the nationality or the country of residence of the headquarters, that does change.
Mhm.
And there's no reason that the US can't be competitive in that space.
So a comment on that, just, and this is near and dear to our hearts right now in one particular industry. Geopolitics matters, unfortunately, far more so than we like sometimes. Solar industry is a very good industry to take as an example. 20 years ago, we had an entire solar supply chain roughly in 3 countries, Japan, US, and Germany. Now it's all in China for the most part. I think 97% of all silicon wafers for silicon-based modules, cells and modules, are manufactured in China. There will be, I hope, sort of an onshoring and a friendshoring of supply chains. This is one candidate. We're already seeing this happen potentially in India. I'd like to see it happen here in the US as well. And maybe that serves as just sort of an example or maybe a catalyst to try and move things a little bit more quickly, because unfortunately we're seeing this sort of, I won't call it deglobalization, but we're seeing a bifurcation, right? We're seeing friends and we're seeing less friendly relationships. As less friendly relationships get exacerbated, you end up with trade wars, and trade wars escalate, and now it's difficult to get things that are required. So that's a very expensive inflationary thing, to onshore, offshore supply chains. My inclination is to think you're going to see a fair amount of this happen over the coming 10, 15, 20 years.
Yeah, interesting. And then I think, given your purview, Steve, like in Jira being a global company, just having these nuances which are region specific and how they will inform as industry evolves, I think will be something to keep an eye out for. Well, this has been super insightful. I could not thank you both enough. I learned a ton in all of this. I'm pretty sure that our audience did as well. And if people were to reach out to you and become more engaged, will you be okay with that?
Sure,
Yeah,
absolutely. Yeah,
Cool.
that'd be fine.
So I think you had your emails in the presentation, and when the presentation is recorded, people will have your emails, and if they're interested, they'll be happy to follow up. Well, with that, I want to thank you personally and everybody who attended, and we'll call in Doug to make the closing remarks. But thank you, Brian. Thank you, Steve. On behalf of all of us, we learned a ton. So thank you for that.
Thank you.
Well, wow. That was really a great set of presentations, guys. And thank you so much for that. A lot to absorb, I think, but we all know this is a pretty complex situation, and it's going to be evolving over time. So we're really looking forward to building on what you've given us tonight and take it forward into the various applications that we see out there for hydrogen, and hopefully we're going to see the birth of a new industry around the world, actually. So that's in itself a very, very exciting thing. So thank you again so much for coming and doing these presentations and answering our questions. And thank you, audience, for coming to us and viewing this as well. We hope you really enjoyed it, and looking forward to doing more of these on hydrogen in the future. So Brian, Steve, thank you. Nitin, thank you for moderating, and you all have a good evening.
Thank you.